So this is the Doppler effect. The Doppler effect shows up in a wide variety of phenomena. The most common one is, so this is supposed to be a car with a siren on top. So this is a speaker, right? And this is, and then this is like a police car, a fire truck car, or something like that. When the car is at rest, these represent like the peaks of the waves. And so when the car is at rest, the waves travel, are spread out equally in both directions. But when the car is going, when the car is traveling, as the waves are being emitted, the car is moving in the direction they're being emitted. And so the waves in front of it are kind of bunched up and the waves behind it are kind of spread out. You can kind of think of, a wave is being pushed out and then it's traveling at the velocity of the wave, at the speed of sound, but the car is traveling at some velocity. We call this the source, and so it's the velocity of the source, right? And then we say the frequency coming out of here is the frequency of the source. And so we want to find a relationship between the frequency observed, what somebody hears who's standing over here at rest, say this car is approaching you, right? Hopefully you're off to the side of the road or something. But if you ever hear a siren go by, it's approaching you, you hear a higher pitch, so you as it passes by you. And so we want to find a relationship between the frequency that this person hears, the observer hears, and the frequency of the source. And the frequency of the source. So this is a frequency that just gets played through the speaker in the car. Maybe it plays an F sharp or something. Maybe it plays a middle C, 260 hertz or something, 262 hertz. And that's just whatever the source plays. But what this person hears depends on what's being played. And so we're going to do it for a moving source and stationary observer. We're going to try to find the relationship between these two things, and then I'm just going to tell you what the relationship is if they're both moving, or if the source is stationary but the observer is moving. You can imagine if the source is stationary but the observer is going this way, they'll be going through the waves faster, and so they'll hear a higher pitch, right? And so we'll derive it for this case, for moving source, stationary observer, and then we'll generalize it to the other cases, right? And so I'm going to start with let's just consider the moving source. So here's my car, right? And here's my speakers. I don't know how to draw speakers, so those are my speakers. And they're bunched up in the front, and they're spread out in the back, because I'm running away from these guys and I'm running towards these guys. And so consider the time t for one full wave to leave the speaker. Right, t is the period, and it's just 1 over the frequency of the source, right? If the period, if it takes a 20th of a second, then the frequency is 20 waves per second, right? And so dW So this wave leaves the source, so these lines represent the peaks, and so we can just look at like this peak or something and say the time, the distance it travels in one cycle is just dw. It's distance the wave travels in time t, and that's equal to the velocity of the wave times the period. Right? That's the velocity of the wave, the speed of the sound, times however long it was traveling. Right? ds equal distance the source travels, also in time t. Right? And so the car is moving this way too. And so the wavelength observed, that is to say the wavelength that's seen, the separation between these curves here, is the distance the wave travels minus the distance the source travels in that time, or it's equal to the velocity of the wave times the period minus the velocity of the source times the period, or it's equal to the velocity of the wave minus the velocity of the source times the period, or it's equal to the velocity of the wave minus the velocity of the source divided by the frequency of the source, because the frequency of the source is just 1 over the period, or 1 over the frequency of the source is equal to the period. Okay, so I'm going to get f0 in here by saying that, look, the velocity of the wave is equal to the observed wavelength times the observed frequency. That's our relationship for any wave. The speed of the wave is equal to the wavelength times the frequency. And so this is the frequency that this person observes. This is the wavelength that's observed. This is the thing we calculated here. And so we can say that lambda 0 is equal to the velocity of the wave over the frequency observed. And so now we can write this way. We can say the velocity of the wave over the frequency observed is equal to the velocity of the wave minus the velocity of the source over the frequency of the source. I just used this equation to replace this guy with this guy, right? And now I'm just going to rearrange this. I'm going to solve for f0, and so I'm going to multiply this side by f0 and divide this side, and you get this. You get f0 is equal to the velocity of the wave over the velocity of the wave minus the velocity of the source times the frequency of the source. And so this tells me the frequency I hear in terms of the frequency the car plays times the velocity of the wave and the velocity of the car. And so I'll do an example of this. Notice that, this number is like 340 meters per second. And this number's cars typically travel 20 meters per second or 30 meters per second or something. And so this is going to be like 1.1. This maybe is 10 times. This is 10% of this, and so this is 1 over 0.9. And so it's just going to be a larger frequency when I'm approaching the observer. Let me just make sure we're clear about that. So I'm measuring in the front, right? That's why I took the difference between these two things. The distance the wave travels minus the distance the source travels. We'll look at the backward end in a minute. But in this example, I've worked out that the forward direction, the distance the car is catching up to the wave in the example I gave, right? And so this is the observer, and this is the source. Okay. So that's our formula, and I'll just do a quick example with that. So we're going to calculate the Doppler effect due to a moving source approaching a stationary observer. And so the frequency of the source, so this is whatever's playing on your siren in your car. It might be an F sharp, it might be, or a C, middle C, it might be 260 hertz or something like that. And we're just going to call it the frequency of the source, right? And then we'll talk about the frequency observed. And so just the frequency, the initial frequency of the source would be what this person would see if the car was at rest, right? But now that the car is moving, this person here is a higher frequency because the waves are bunched up, and when they go by quicker. They've got a shorter wavelength, and so he gets a higher frequency out of it. You remember the relationship between the velocity of the wave is equal to the frequency times the wavelength, right? And so we could say, look, the velocity of the wave, I'll just write them over here, the velocity of the wave is equal to the frequency of the source times the wavelength of the source. That's with the car not moving, right? And then the velocity of the wave is also equal to the frequency observed times the wavelength observed. So in this case, the person is going to see a shorter wavelength and a larger frequency, so that the product of the two numbers stays the same. And so we'll just calculate these. And so first I'm going to say, look, we'll consider a time period t for one cycle. In other words, let's say these lines represent the peak of the wave that's coming out, right? And so the period t is the time between when one peak comes out and when the next peak comes out, right? And so it's the time between any two of these guys, right? And so so the distance the wave travels in that time how far the wave goes is just the velocity of the wave which is equal to the velocity of the wave times the time, right? The distance the wave travels is just the speed of the wave times the time, right? The distance the source travels, which is the car, is the velocity of the source times the time. And so the wave moves, but the car is catching up to it as it's getting ready to emit the next wave. And so the wavelength observed is just the distance the wave travels minus the distance the source travels. In other words, how far the wave has gotten out here minus how far the car has gone before it's emitting the next wave, right? And so what is that? That's the velocity of the wave times the period minus the velocity of the source times the period, which is equal to the velocity of the wave minus the velocity of the source times the period, right? Well, the period is related to the frequency of the source by this. We already said the period is 1 over the frequency, and so we can say this is just the velocity of the wave minus the velocity of the source over the frequency of the source. And so we're looking for a relationship between these two guys, right? And so far we have this. We have the wavelength observed is equal to the velocity of the wave minus the velocity of the source over the frequency of the source. But if I use this equation, I can say that's equal to the wavelength observed is equal to the velocity of the wave over the frequency observed from this equation. And so that means that the velocity of the wave over the frequency observed is equal to the velocity of the wave minus the velocity of the source over the frequency of the source. So I just plug this guy in here, and now I've got a relationship between the two frequencies, which is what I'm after. And so I can rearrange this, and I won't go through the algebra of that, but it's not hard. Just multiply both sides by f0, f observed, then multiply both sides by f source, and then divide both sides by velocity of wave minus velocity of source, and you get the frequency observed is equal to the velocity of the wave minus the velocity of the source over the velocity of the wave times the frequency of the source. And so if I know the velocity of my source, the frequency observed is equal to the velocity of the wave over the velocity of the wave minus the velocity of the source times the frequency of the source. And so if I know the velocity of the wave and the velocity of the source, in other words, how far what's the speed of sound, what's the speed of my car, then I can just multiply that by whatever the frequency my car plays, and I know what the observer will hear. And so I'll do in a couple of examples of this. And then when I get done, I'm going to generalize this to say, well, what if the observer is back here? What frequency are they going to hear behind the car, after the car passes? Remember, when a siren goes by, as it's approaching, you hear a higher pitch, so you hear ee-oo. And so after it goes by, you hear the ooh, the lower sound. And so actually, the only thing that changes is this minus sign becomes a plus in the backward direction, so I would have a plus here. And then I can generalize it to when the source is stationary, but the observer is moving. And so if I'm running towards the car and it's stationary, I still hear a higher pitch, or if I'm running away. And so there are really 4 equations, and we'll write them all down. But first I'll do an example with just this one. So an ambulance, which is a siren of frequency 400 hertz, travels at 30 meters per second towards an observer who is at rest. So here's my ambulance. Right, maybe I should have a little taller cab in there, maybe like that. So it's playing a frequency, F0 is 400 hertz. Sorry, F source is 400 hertz, not 4,000. 400 hertz, right? That's the frequency of the source. And it's traveling, the speed of the source is 30 meters per second, right? And so I've got some listener, hopefully it's somebody standing off the side of the road just watching the ambulance go by, right? And so we want to know, what is the observer here, right? And so this was our formula, right? It said the frequency heard by the observer is equal to the velocity of the wave over the velocity of the wave minus the velocity of the source, right? Since it doesn't give us any details about the temperature or anything for us to calculate a different temperature, we're going to say the speed of sound is the speed of sound at room temperature, 344 meters per second, or something like that, right? And this is times the frequency of the source. And so this formula becomes 400 meters per second, 344 meters per second over 344 meters per second minus 30 meters per second times 400 hertz. So I can right away say that the formula looks good because this number is going to be a little bit greater than 1, which means I'm multiplying this by a number that's a little bit greater than 1. And so it's going to increase the frequency, and that's what I expect it to do. And so it's 344 divided by 314 times 400. And I get about 438 hertz. So now we can ask the question, what happens after the ambulance passes, right? What frequency does the observer hear? So we didn't talk about this, but we mentioned last time that this minus sign changes into a plus sign. And that's because whereas the waves get crunched in the forward direction, they get extended in the backward direction, because the sound still travels at the velocity of the wave, but the truck is moving away at the velocity of the truck, and so instead of catching up to the waves, it's spreading them out. And so this becomes a plus sign, and we get the frequency of the observer is the velocity of the wave over the velocity of the wave plus the velocity of the source times the frequency of the source. And so this becomes 344 meters per second over 344 meters per second plus 30 meters per second times 400 hertz. Right. this is what I expect to see. I saw a higher frequency when the truck was approaching me, and after it's leaving me, I see what's behind it, and that's a lower frequency, and that's this guy. And so those are our two formulas. So the Doppler shift for a moving source and a stationary observer is this. It's the frequency observed is equal to the velocity of the wave over the velocity of the wave minus the velocity of the source times the frequency at the source for an approaching source. And then the frequency observed is equal to the velocity of the wave over the velocity of the wave plus the velocity of the source times the frequency of the source for a receding source. Often we'll just write that this way. We'll say frequency observed is equal to the velocity of the wave over the velocity of the wave minus plus the velocity of the source times the frequency of the source, where the top sign is approaching and the bottom sign is for receding. So now we can talk about a slightly different version of this. We can say, what about the Doppler shift What about a Doppler shift for a moving observer and a stationary source? So now my, if you want to say it, now my ambulance, draw a better ambulance. Is just stationary, right? It's got speakers on the back, and so it's putting out equally spaced waves forward and direction and backward. But my observer, right, is either running towards, so he's going through more waves than he otherwise would if he was standing still. And so for this case, the frequency observed is equal to the velocity of the wave plus so if the observer is approaching, the derivation of this is very similar to what we did for the previous case. I just won't do it similarly. Like that. If I'm running away, I'm going to hear a lower frequency because the waves don't catch up to me as fast because I'm moving away. And so I'll have a number that's slightly less than 1 multiplying the frequency. So I'll hear a lower frequency if I'm running away. I'll hear a higher frequency if I'm running toward. And so you can combine these two equations. So I'm going to write a single equation down for the whole thing. Here I'm going to say So this is the formula. You use the top sign if they're approaching. So if you had, for example, an observer that's approaching, say the source is over here, the observer is going this way, and the source is approaching the observer, it's going that way. Then when you use a plus in the top one and a minus in the bottom one. If the observer is approaching the source, but the source is running away from the observer, you would use a plus sign in the top, in the numerator, and a plus sign in the denominator. And so this is, probably what you'd see on an equation sheet or what you'd want to write down to keep track. And you just have to remember to use the plus sign when the observer or the source, the top sign when the observer or the source is approaching the other one, and the bottom sign when they're moving away from the other one. And so let's do an example with that. So a bird sings a note at 300 hertz while flying away from its mate at 20 meters per second. The mate is flying in the opposite direction at 30 meters per second. What frequency does she hear? Right, and so this was our formula, just the general formula is velocity of the wave plus minus the velocity of the observer, the velocity of the wave minus plus the velocity of source times the frequency of the source. Well, this is going to be our source frequency, right? And so again, we'll use the velocity of the wave since we don't say anything about it. We'll just use 344 meters per second. If they give you a temperature of the air or something, you might have to do that calculation 20 times the square root of the temperature in Kelvin to get the speed, but since it doesn't say anything, just use this one. And so this is the velocity of the source, right? But it's flying away from its mate, so top sign is approaching, bottom sign is receding, so I would use a plus sign here, right? And so I'm going to have velocity of the wave plus the velocity of the source, because the mate, it's flying away from its mate, and the source is in the bottom here, and so the bottom sign is for receding. Similarly, for the numerator, I'm going to say the mate is flying in the opposite direction, and so I have one bird. I don't know how to draw a bird. So here's a bird. This is a source, right? But it's going this way. Velocity of source. Well, this is the mate, and it's going this way. That's the observer. And so they're both receding, and so that means it's the bottom sign for both, and so it's minus velocity observer times the frequency of the source, right? And so this is the formula that I use for this one. I'm going to have to erase my diagram, right? And so that means the observed frequency is 344 meters per second minus the velocity of the observer, which is 30, over 344 plus the velocity of the source times 300 hertz. Right, and so that's 314 meters per second over 364 meters per second times 300 hertz. So 259 hertz. If the bird had a good ear, it could know which way the bird was flying relative to it by the pitch of the sound that it actually heard. So just a few things about the Doppler effect. The Doppler effect is widely used. It can be used in measuring the speed of cars on the highway. A radar gun will bounce a signal off your car, and it'll measure the Doppler effect to tell how fast your car is going. The Doppler effect is used with sound in sonograms in your body. It can tell how your blood's moving in the vessels in your heart, whether your arteries are clogged. It's been used with great effect in astronomy to figure out how objects are moving in the universe. In all of these cases, you have to know the source frequency, and so in distant galaxies, we can tell that the source is largely hydrogen. We can pick out individual, if we're looking at a distant galaxy, we can tell which light sources were from hydrogen atoms, so we know what their frequency is when they're stationary. And so we can measure the Doppler shift on them. That is to say, we can measure the observed frequency, the frequency we see, and we know what it should be, and so we can use that to solve those equations for the relative speed of the galaxy. So, for example, if we have a galaxy that's receding from us, then and we view ourselves as stationary, we just want to know the velocity relative to us, then we would go back to the first equation we got, the velocity of the wave minus the velocity of the source times the frequency of the source. Right? We could rearrange this equation and solve for the velocity of the source, and so it's a little tricky, but you kind of do it this way. You say, well, I'm going to move the frequency of the source to the other side and the velocity of the wave to the other side, and so I'll get frequency observed over the frequency of the source times the velocity of the wave equals 1 over the velocity of the wave minus the velocity of the source. Right? I've just divided both sides by velocity of the wave times the velocity of the source, and then I can invert both sides, and I get the frequency of the source times the velocity of the wave over the frequency observed is equal to the velocity of the wave minus the velocity of the source, or I can say that the velocity of the source is equal to the velocity of the wave times 1 minus the frequency of the source over the frequency observed. If you just sort of work through the math on that, you should be able to do that. To get to here, I just move this to the other side and move this back to this side, and that gives me velocity of the wave minus the frequency of the source velocity of the wave over the frequency observed, and I just factored out the velocity of the wave. And so for light, we kind of know all of these, right? We know that one, and if we know the frequency of the source, which like I said is hydrogen atoms, and we know the observed frequency, that's just what we measure with our telescope, we can tell how fast galaxies are moving. And these measurements, they're slightly different with light, but it's close enough to make the discussion, that led us to understand how objects are moving in the universe, that all the galaxies are moving away. It's what led to the expanding model of the universe. But there is a wide range of applications, as I said, in medicine and in just the motion of objects around. Sonar can be used for submarines and all kinds of things, and we can use these shifts to measure velocities and just inside your body, outside your body, in outer space, in different places.